Good morning, students. We have already discussed displacement time graph and velocity time graphs. And now comes the acceleration time graph, how acceleration varies in time. There are many situations. We have discussed those situations in relation to displacement time graph and velocity time graphs. And now we are repeating the same situations, same circumstances. For example, what should be the acceleration time graph for an object that is dropped from a small height? Because this is oft repeated question in the exam, the most commonly discussed situation in various questions. An object is dropped from a small height means the acceleration is constant. So for an object dropped from a small height, acceleration time graph will be two axes, A on this side, T on this side, and constant acceleration means it's a straight line with zero gradient. That means there is no variation in acceleration with time. The object is dropped from a small height. Its velocity increases uniformly. Therefore, its acceleration will be constant. So this will be the shape of that graph. Of course, if you repeat this graph with the velocity time graph, with displacement time graph, that will also be useful. If I go back a step and remind you what was the velocity time graph for the same situation, it was this straight line. That means velocity is increasing at a constant rate. So velocity time graph has a straight line, but with a gradient equal to 9.81, and acceleration time graph will be a straight line with gradient equal to 0. Both these graphs represent the same situations. This is the velocity increasing at a constant rate, and therefore the acceleration has remained constant. If I compare it with the displacement time graph, that will also be useful at this stage. Displacement time graph simply means the position of the graph. Let's see, this is xt graph. The displacement is increasing with time at a uniform rate. So this will be a curve up. So displacement time graph simply shows that the rate at which the position is changing is increasing at a constant rate. So a curve upward simply means a velocity is increasing at a uniform rate, and that means a uniform acceleration, which means a straight line. So a displacement time graph, as I discussed in the beginning, it's always a curve up if its velocity increases uniformly because this is a curve which is smoothly varying up. So this must be a uniform increase in the gradient, and therefore a uniform increase in the velocity. On the velocity time graph, it's a straight line because in equal intervals of time, we observe equal increase in velocity, and therefore this result. So for a small, for an object dropped from a small height, we have these three situations. But how do these graphs change if instead of a small height, we make it a large height? From a large height, acceleration will no longer be constant as the object falls from a large height. In the beginning, the acceleration is large because the object starts falling with the same 9.81. But as the object falls a few moments, the air drag becomes significant so acceleration starts becoming smaller. So in so many questions, often in the multiple choice, they ask this question: what will be the shape of the graph for an object dropped from a small height? It is the acceleration. Let's say it starts here in the beginning and then it drops. And with time, the acceleration becomes very, very small. It may drop to zero, but not necessarily. If the object is dropped from too large a height, maybe it attains the terminal velocity, then acceleration may become zero, but that is a special case. Generally, the acceleration starts from a certain value, so you can decreasing the acceleration of the object, although it speeds up, but not at that rate at which it was speeding up in the beginning. How will this graph change? If an object drops from a very large height, it will be a straight line for a few moments in the beginning, but very soon it will take a curve and then it will become almost a straight line. So an object will not be accelerating uniformly anymore a few seconds after we have dropped, because the air drag is becoming significant. Its rate of increasing velocity is not same. It is decreasing gradually, and ultimately the object becomes starts falling with a constant velocity. How will the displacement time graph be affected? We have a curve in the beginning, maybe up to this point, but then there will no more be an increase in velocity and it becomes a straight line like this. So yes, a curve in the beginning, and this curve simply means that there will be an acceleration and then that curve will become smaller. In the beginning it will be a significant curve, and then that curve will become gradually straightened and ultimately a straight line. So generally this is the shape of the graph for displacement time graph if an object is dropped from a very large height. So this part is significant because this means the object starts falling with a constant velocity moments after it is dropped. And the same picture is shown in this because acceleration becomes more or less constant. So this part needs to be understood. So this is what happens when an object is dropped from a very large height. Now, let's discuss a few other situations. Like velocity time graph, displacement time graph, and acceleration time graph also has two sides, positive and negative values. We have this in displacement time graph, we had this in displacement time and velocity time graph. Acceleration time graph shows change in direction in acceleration. So if an object is moving at a constant acceleration and then suddenly it changes its direction and moves with a constant acceleration, but in the opposite direction. This is a possible situation. This may be an object moving between 2 points. It may be an oscillation, but the requirement of this oscillation is that the object must be moving at a constant acceleration, moving to this side, and then to this side it moves. And we have two values which are same in magnitude but opposite in direction. So object may have an acceleration going this way and then it may be accelerating at constant rate, means there is no change in its acceleration, its velocity is increasing, but suddenly due to some mechanical system maybe, or maybe it is a radio controlled device that is you are playing with, it starts decelerating. That means its velocity decreases at the same rate. That means the acceleration changes its direction. It becomes negative, because negative acceleration often means deceleration. So this is acceleration, this is deceleration. If I want to show this on the velocity time graph, what should it look like? It may be if an object is dropped from a small height, it accelerates. But let's say it hits the floor and moves up. So during this hitting the floor, let's say it doesn't take any time. But if moves up again after the rebound, this is how. If this is the part of the graph which shows constant acceleration. But let's say an impact has taken place here, and due to this impact, the velocity has gone to this direction, and the object will so this is when the object moves in the upward direction. So it decelerates, and ultimately its velocity becomes 0 at this object. So during this time, the object is accelerating, falling freely, making an impact here, and almost instantaneously it changes its direction and starts moving up. But during this time, the acceleration is downward, so it decelerates. So the deceleration is shown with negative side. So this could be the shape of the graph during the bounce. So it may be a sudden change in velocity, and therefore the change in direction of the acceleration. So acceleration time graph could be like this. This could be the shape of the velocity time graph. Because acceleration time graphs are not many in the exam, there are very few situations like I have discussed. There are not many questions that you will see about the acceleration time graph. It's mostly velocity, velocity time and displacement time graphs. So this introduction should suffice for you to try a few questions. Let's move on to the main topic for today, and that is projectile motion. In this topic again, we'll be talking about displacement time graph, we'll be talking about velocity time and how the acceleration changes. So we'll revisit these concepts again and again during this topic also. In projectile motion, there are two situations, two types of questions in the exam about projectile motion. Projectile motion is actually a two-dimensional motion in which an object takes a curved path when you throw it at an angle up or from a large height. It follows this path. Let's say you have thrown a stone horizontally like this. It will follow a curved path and fall below this. Let's say this is the roof of a building, and you have dropped something. Initially, the direction of motion is this. So this is initial direction of motion of the object with let's say certain velocity. I assume this is 4 meters per second. And you have dropped it from a height of, let's say, 10 meter. So this is one type of situations. There are many questions in the exam in which they give us the height and they inform us that the object is being thrown horizontally with initial velocity 4 meter per second. The object takes a curved path and hits here, and it hits here at an angle to this surface, and this is the final velocity v with which it hits the floor, hits the ground. So an important thing about projectile motion is that throughout this motion, if this object is considered here a second or two later, it will have a velocity in this direction now. Naturally, it will change its direction. So velocity is entirely horizontal in the beginning, then it changes its direction, and then it changes its direction again, and it changes its direction here as well. So it continues changing its direction until it hits the ground. The important thing is that at all positions, the horizontal component of velocity remains 4 meter per second. Even on hitting the ground, it is exactly 4 meter per second, the horizontal component of velocity. But what about the vertical object which is dropped from a small height increases? That means the rate at which the vertical component increases is same 9.81. We don't have any vertical component here, so initial vertical component of velocity is equal to 0. And since acceleration meter per second square, vertical height is 10 meter. So this gives us a clue, and the clue is, if I consider this motion having two components and treat two components independently of each other, I mean the vertical component can have its own rate of increasing. So if I want to calculate this component, the vertical component of velocity with which it hit the ground, I can apply the first equation of motion on this situation alone. If I want to know what is the vertical component of velocity, this is Vy. So let's say the final velocity along the vertical, and I apply the first equation of motion, u plus gt. This is 0 because along the vertical direction there is no initial velocity. So this 4 meter per second is not the velocity along the vertical, it is along the horizontal. So the point I'm trying to make is that when you have this situation, let me call it case 1, in which an object is thrown along the horizontal from a height, any given height, the initial vertical velocity is taken 0, acceleration is taken 9.81, and if I know how much time it has taken to reach this, I can easily find out the vertical velocity with which it will hit the ground. In order to calculate the time it has taken to reach here, I go back and have this equation. S is equal to ut plus half gt square. This is the initial velocity because I'm applying this equation along the vertical, so this is 0. This is 9.81 and this is the displacement of the object along the vertical. So 10 is equal to this, of course, 0, and this is 1/2 into 9.81 into t squared. So this is 20 over 9.81 under root, and that is t. And this is approximately, if you use the calculator, this is 1.14 second approximately. If I use this time here, I can find the final velocity with which it has hit the ground. So Vy is equal to 0 plus 9.81 into 1.14, which is approximately let's say 16 meter, sorry. This is 11.6 meter per second. This is the velocity with which the object has hit the ground along the vertical. So I have this component now, and I have this component now with these two components known. Let's say this is 11.6 that I have just calculated, and this is 4 along this. So I have a rectangle. So this is what the resultant velocity should be equal to. So using Pythagorean, you can calculate 11.6 squared plus 4 squared under root. This will be the final velocity of the object with which it hits the ground. So projectile motion is the motion of an object in which the object takes a curved path, and in this motion, velocity remains constant in one direction and acceleration is constant along the other. It has two components throughout the motion. I repeat, projectile is that type of motion, a curved motion or a two-dimensional motion in which velocity remains constant in one direction, which is horizontal, and acceleration is constant along the other, which is vertical. So you have two components always, and one component is always considered constant. Why it is constant? Because there is no force acting on this object along this direction. Even air drag is ignored. So there is no increase or decrease in velocity along the horizontal. However, along the vertical, there is a force acting, and that constant force results in a constant acceleration. The object is pulled down at a constant rate. So I can treat the vertical motion independently of the horizontal motion. This is an important point about the projectile motion, that the two different components of velocity can be dealt with, can be treated, can be taken independently of each other. Like I take initial component of velocity and then I put it in the first equation here. And if I know how much time it has taken to come to this, an important thing is that this time and this time is same. If you throw an object in this direction, it will reach here in the same time as the object that you have dropped here simultaneously. So an object that comes from this point and drops straight here will have exactly the same time taken as this object, although it is hitting many meters away from it. So this time is same. Therefore, this time, whatever it comes out to be, if it is 1.14 second, although it is the time that this object is taking to reach here, I can use this time to calculate the vertical component of velocity here, assuming that it is the same time that an object should take if I drop it from here and it comes vertically hitting here. So I have a few points. I have tried to explain a few points in this discussion. Let me make those points clear by writing them separately so you know for future. Case 1, when an object is thrown horizontally from a height, from a certain height. So in this case, and in all other cases as well, horizontal component of velocity will be constant. Horizontal component of velocity will be constant. So if they ask me to show the velocity time graph of the horizontal component alone, what should be the shape of this graph? This is the horizontal component of velocity, so I write it VH. This is time. What is the shape of the horizontal component of velocity in time? Since it remains constant always, so whatever its value in the beginning, that will remain the same. However, vertical component of velocity, vertical component of velocity increases uniformly with the same acceleration, 9.81 meter per second square. So if they ask me to show the vertical component of velocity, VV, that will be this shape. So it is the same graph that we learned for an object dropped from a small height. So vertical component of velocity increases uniformly at the same rate at which the acceleration with which an object falls freely if it is dropped from a small height, the same acceleration, 9.81. So it is the same gradient. However, the horizontal component remains constant, so that will be a straight line along the horizontal. The time that an object takes to reach the ground is same as the object, the same time as an object would take that is dropped from the same height and it falls vertically. The object, or the projectile in this case, the projectile, it may be a bullet, it may be a stone that you have fired, it may be an arrow you have thrown with the bow or anything, but it is initially moving in this direction and then ultimately it follows a curved path that projectile, if it is in case 1, which is thrown from a large height, from the roof of a building, it takes the same time to reach the ground, as an object dropped from the same height, falling freely along the vertical. Which means, let me show with the figure again. Suppose you have thrown that object from this height. This object, of course, takes this path and it hits here. And at the same time, you have allowed an object to move freely in this direction. That means you have dropped it like this. So an object dropped and it falls freely and goes to the ground. It takes the same time as this object that is thrown in this direction and hits the ground several meters away. These two objects will take the same time to reach the ground. So this is an important trick in handling projectile motion, because we often calculate the time this object takes to reach the ground level by assuming that initial vertical component of velocity is 0. The acceleration along this direction is 9.81, as I just did in the question we have just discussed. So if I know the displacement, I quickly calculate what time it should take, because initial velocity is 0. So second equation of motion is really helpful in those situations in which you are calculating the time to reach the ground level, if this is the kind of projectile motion we are talking about. I stop here. This is case 1. I'll share a few simple questions with you today, or maybe tomorrow. I'll upload the worksheet related to this. These are important points to remember, and the question we have just discussed, go through again with all its minute details. Try to link these facts, try to understand them, and then apply it to a couple of questions. We'll have many more such questions discussed here in the coming classes. Thank you for today.